I'm going to speak about incremental language processing and how it enables faster and better responses. And I want to clarify that title a little bit. Or maybe. I'll have to do so much multi-clicking now. It's going to be really fun. No, that's easier. Like the first thing that I must mention is that I mostly work on spoken. So once I figured out how to work this, it will speed up. That I mostly work on spoken language processing, in particular spoken dialogue, or actually anything that is spoken language in very interactive situations. And the reason why I put spoken in there is actually because I think language is much more interactive when we're speaking, because it's way beyond words and there's so much more subtle things in there then. The second aspect is, still sorting it out, I'm working on faster responses. I put it here because that's part of the punchline. But actually what I'm working on is responsiveness. So that means kind of responding quickly to the user, and that is my goal of what I'm doing. And there's this nice quote by Nigel Ward saying dialogue interaction is an intricate dance. So dialogue is actually not a ping-pong game going back and forth, but dialogue is a very fluid thing as it progresses. So it's not he says something, she says something, but it's very tightly knit, in my opinion. And that's the important things. And then I'll also talk about incrementality. But incrementality is actually just a processing paradigm to achieve this goal. Incrementality itself doesn't matter. If we had a different way of achieving these goals, they would be just as good. I think responsiveness in dialogue and interaction is actually the crucial and interesting part. And incidentally, we frequently get better results or even better responses, I'll talk about that later, when we work incrementally and enable more responsive interaction. So let me start out by an example by what I mean about this responsiveness and all this, and compare that to what systems would do. By looking at a wintry scene in northern Germany, my hometown, somewhere between the computer science campus and the main campus, and I might be sitting in a car and an in-car navigation system might say, next, turn right after 60 meters, because that's roughly 180 feet, or roughly 60 yards. So where am I supposed to go? Actually here. But the question is actually, where is 60 meters? And the question is more relevant because saying this will actually take 35 meters at a reasonable driving speed. I'll have to advance this guy. What I'm saying mainly is that spoken language unfolds in time, and that's actually not a problem, but it's also the solution to the problem, to the very problem. Because the way humans react, they're very responsive in what they're doing. And they're responsive in different ways. A, they might internally replan. So I might just go from turn right behind the traffic light to something like turn right, well, more like straight, because I never knew that this counted as turning right here. Or saying something like the second. So internal replanning might be a reason for responding to the situation. Or external events could be a reason. So I could say, follow the blue compact. Because that's actually, that car is going where I want to go, and if I know that already, it might be convenient to relate to this external event. Or I could respond to the interlocutor, so the driver in this case. So for example, the driver's behavior, if the driver were to slow down here already, I might say something like, later, behind the light. Or of course, we're talking dialogue, I might respond to the interlocutor's spoken feedback, which might say, behind the light, and then I could say, yeah, behind the light. I'll have to advance here a little bit. All right. So that's how humans would handle this situation, and the dialogue system would instead play this ping-pong game rather than being fluidly responsive. So the fundamental assumptions that I have in my work is that speech unfolds in time and that the world may change during this time, right? While I speak, but also while I listen, of course. I guess I defined responsiveness quite well already, and the solution to this whole set of problems is actually incrementally processing speech while it happens, rather than processing a stretch of speech, then doing a response, then listening again, but rather instead doing all of this concurrently. So this is a kind of an outline of the talk. I hope I've convinced you that responsiveness in interaction might be an important thing. I'll then talk about the concept that I use a little more, introduce a data model for incremental processing, and then talk about some examples of responsive systems that we built in the past. Who in here is in Casey's class, in Dr. Kennington's classes, or previous courses? So you all know this stuff anyway. Might still be interesting. Do yawn if it gets too boring, then I'll just skip ahead a little bit. So be responsive as well, right? Good. So I'm going to put up a definition of incrementality here. So the first thing is an incremental processor consumes input and generates output in a piecemeal fashion. What does that mean? It's kind of like you have a large thing and you can divide that into smaller things and you work based on these smaller things. That tended to be the definition for incrementality until I figured out, well, it also has to sometimes generate output before input has been completed. Otherwise, there's no external effect. It might be doing something internally, but we wouldn't know about it. It doesn't really help us. But it doesn't always have to output something just because it got some input. But it might be more better in the situation to actually to aggregate some input before it outputs something. Let's try to look at an example here, and I apologize, my computer and LibreOffice don't work well together for a half year now, and I guess the next Ubuntu will fix that. So let's compare incremental with non-incremental processing, which is kind of like this decoupled mode of processing. There we might have some input, and that input would go into the processing module. Then it will trigger some processing within the processing module, produce some output, and then the output is passed on beyond the processing module. So, of course, processing takes time. We can't avoid that. So there will be a small delay for this one processing module. In the real life, we'll have multiple processing modules chained together, so all these delays will add up. So if you look at your standard dialogue system, we'll have something like speech coming into the system, the speech recognizer turns that into words, some understanding component turns that into a dialogue act. But dialogue act is processed by the dialogue manager, maybe with more modules coming into play, passing on a dialogue act about what should be done. This dialogue act will have to be verbalized by a generation component. That generation component outputs words. These will be synthesized into speech. So we might have tiny delays at every step, but in total it's going to be a long delay. And what's worse is that it's actually impossible in this model to output anything before the input has ended. And that's actually what I found most disturbing, that you can't interrupt people because this thing isn't done yet. So that's annoying. In incremental processing, the assumption is that you have input that can be subdivided into parts. And then these individual parts, if they appear here, will be consumed one by one. So conceptually, all the input is there. Let's just think into the future. But at this point in time, we only have this input. And that input will be consumed, and some output will be generated based on that, if I'm lucky. Yes. So these inputs have been output already. Now we are waiting further output from the processor, and this goes on a little bit until finally we are done with the full thing. just about now. Maybe. This is really weird. So that's what incremental processing is about. So in an incremental system, we have all these individual modules that are able to output something, partial hypotheses we call them, based on partial input. And that way we can give feedback while we're still listening. We can take actions, like, book the flight already, or we can barge in on the user before they're done. Because that way we are like very close to what's actually to the present, right, and how we act. There are some limitations, of course. I mean, there's a reason why people usually wait to the end. We're missing context. So everything that we do will be based only on what has been seen so far, and of course later input may result in changes. And I believe Casey uses the exact same example in his classes. This is SAMPA. It's kind of like the International Phonetic Alphabet for computers. So this kind of like indicates 4, and then I get more input. So at this point I'll think, oh, this sounds like 4. Then I get some more input, like T, and what's that going to mean? It sounds like 40, right? 40. Together that sounds like 40. Now we get more input. What should we think? Yeah, probably 14. And what happens when we add that? Yeah, that's ages. So we're actually back to the start. We had 4 teenagers. I failed to come up with something that, given ages, would give something that goes back to 14 or 40. But this is just an example of how context helps us to disambiguate the past. So we need to cope with the fact that we're missing context. So one thing that's also crucial to think about language, more language than speech, I think, is that language is non-local. There are linguists in here. Who has seen this sentence? Oh. Yeah. A few of you have seen it. Do you agree to my put the speech tagging below?
Yes.
You do for now. For now you do. So the horse raced past the barn. This is a determiner. This is a noun. This is the verb. I have no clue what that is. Anyway, doesn't matter. So now in the future, some important linguist comes up with another word here. The horse raced past the barn, fell, and we actually have to change our analysis of what's going on. This is actually the main verb. And the horse is being raced past the barn, and while doing that, it falls. Poor horse. I didn't remember the name of that horse down there. Should have changed that in the slides.
The Bronco.
The Bronco, yeah. The Bronco, yeah. Okay. Should have changed that, and then it would be a unique sentence. So the message that I want to get across is just waiting long enough doesn't cut it. Where for this speech example, you could say, well, just don't think about whether it's 440, 14, or for teenagers. Just give it a little slack. But language is actually non-local. So there could be, I could be talking in a subclause about this barn forever, as long as I wanted, until I add or don't add the full verb at the end. So just waiting doesn't cut it. But instead, we actually need to be able to support revisions to output. So rather than saying, okay, we'll wait and only output this after we're sure that this is the main verb in the sentence, that doesn't work. But we must be able to output it and later say, nope, sorry, I was wrong. I thought that, but it's actually wrong. So we must be able to support that for output. Of course, the second module, receiving such output, will also have to deal with such input. Right? So the modules actually have to cater for changes in their input. They have to kind of be able to track what they thought based on the previous input and relate that to what they actually want to do. Luckily, we came up with a data model for that, where the which is based on the incremental unit model, where an incremental unit is actually a minimal amount of information or some sort of unit of processing on some level of abstraction. So say for text it could be words. For spoken words it could be speech sounds. For speech sounds it could be tiny slices, this is a technical view, tiny slices of audio that you then kind of turn into a speech sound or that constitutes the speech sound. And these units are interlinked. So they aren't standing alone, but a word consists out of a set of phonemes or a sequence of phonemes even. And a word probably has a word following it, and the word constitutes some meaning, and so on. So all these units are interlinked. And that network of units is actually the information state of the system. So we have implemented that in InproTK. InproTK is kind of old. I wouldn't recommend it if there weren't a local hero here that you can direct all your questions to it. And the nice thing, it unifies this incremental input and output, and thanks to Casey, all the things in between as well. So I talked about the information state, this IU network. So we have, in this network, we have different types of information on different levels of abstraction. And then we have these links to trace input dependencies and output dependencies likewise. So the grounding. Now over time, as time goes on, we will edit the network, which is as results of belief changes. For example, we get more input. We add the T or the N to our word, and this kind of means we have to, the next module might have to revoke a prior hypothesis and replaces it against something else, and this might trickle up in the system. Or we could also have the case where higher level reasoning says, no, this is impossible. You can't be talking about 4 teenagers in this domain, and crossing out this up here, and that kind of forcing lower level modules to reconsider what is possible. So giving you another view of the same thing, here, if I have here time moving forward and the level of abstraction going up, and that slide, oh, I'm behind here. Sorry, people on the internet. Damn. Casey, can you rescue me? Okay, cool. So what we have here is we have some input, speech coming into the system. I think I pressed on home. That was wrong. So I might understand the word put based on that and consider, okay, this could be the semantic meaning, put. And then I add more audio, and the speech recognizer will come up with, oh, this might be meaning the, and then I add more, which might come to the meaning cross, some meaning representation, and higher up some pragmatic representation. Oh, if I want to put something, I probably want to put it somewhere, right? Putting it from to. And basically what you see here is, is kind of a triangle where I'm lagging behind more on higher level representations. Nice, good job. So I'm lagging behind more as I go up in the hierarchy of abstraction. And then when I consider the same for output, I might have a rough idea about what I want to say. Something like, okay, I want to acknowledge that I can take X, or that I will take X to put X somewhere. So if we go back to this one again, if someone tells me, okay, please put the cross, and I can already go ahead and say, okay, I'll take it to then put it somewhere. And I can actually start, down in the hierarchy here and say, okay, I'll take, without needing to know what I'm taking, although I actually, in this example, would already know that it's the cross. And on the lower levels of abstraction, there is actually no need to think about how to pronounce take, and as a speech synthesizer actually coming up with the exact words, take, because it's so far in the future anyway. Let's bother about it in half a second, not now. And that's generally my functioning actually. So we have the same triangle but pointing in the other direction there, where we have to have a broad view into the future, what might be going on, but it can be underspecified. And then we have to be more concrete, as we're not looking far into the future but into the immediate future. And so on top you need to have some decision making that unifies these two sides, input and output, saying, okay, if I first need to grab something if I want to be able to put it somewhere. And then as you have all these links in here, you would, in this example, know that X is actually the cross, because that's what X is over here. Okay. So this is the data model. At present, it's kind of like looking very much, like one end and the other end. One thing that we want to move to in the future is to bring these things together, because it's kind of funny, the speech recognizer and the speech synthesizer, which do the same thing in a system, just in different direction, are actually maximally apart in systems. So the vision is kind of to bring these layers closer together, speech, language, and content. Content already is one thing usually, but language understanding and generation usually is two different things as well. And speech recognition and synthesis are also radically different modules, and for good reasons, but to bring them together to handle to deal with speech, likewise to deal with language here, because if you look back at this example, here I might have said the cross, but I could also be saying the plus sign or something, which looks reasonably close to a cross. Then it might be wise to not verbalize this as cross, although the semantic meaning is the same, but to verbalize that as the plus sign, because that's what the user just said. It's kind of like keep these things that are similar layers together. Then, so that was the theory. Now we're going to watch movies. Much better. I brought two movie examples and then an example about movies. So I have a few examples. One is to play puzzle games with these beloved pentomino pieces. So the question here is, how do we puzzle an elephant? And basically we designed it as, okay, you do two things, you take a puzzle piece and you put it somewhere, and you take the next puzzle piece, you put it somewhere, and so on. And the main challenge here is referring expressions, because these puzzle pieces are kind of difficult, and we worked with these quite a bit. You can simplify it by reducing the set, by assigning reasonable colors, and so on. In any case, it's just a maximum of 12 different of these pentomino pieces, so that's fairly easy. But then you want to put this puzzle piece somewhere in the elephant, and there's actually not infinitely many, but quite a few of possible positions where you might want to put the puzzle piece. And now we could reduce that set by saying, okay, if we want to puzzle the elephant, what even makes sense? But that would probably reduce to the point of just solving the puzzle for the user, which is not the point here. So we want the user to be able to kind of say where to put the puzzle piece, and be able to put it here, 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 and so on. Too many. And from our work in this area, from actually having humans puzzle these things, we also know this is highly game dependent. So people will talk about the trunk for an elephant, but not for elk. They will not say trunk there. So you end up with radically different vocabulary, and that is actually annoying to design such a system. Whereas this setup here is kind of closed. So what we decided was move this complexity of natural language understanding and potentially generating for the system to be able to say, yeah, this area down here, I'm going to refer to that. And humans have a really hard time of referring to this puzzle piece, actually. Move that from the natural language understanding and generation to the interaction loop. So be more interactive, be more responsive, and instead of naming, try to go towards steering. So the user is actually steering the computer to do things. The underlying principle is affordance here. So affordances are conventionalized attribute meaning pairs that manifest possibilities of interaction. This means things allow you to do things. So for example, a door can be opened. So if I see a door, I might feel the urge of opening it. Actually, we had that earlier. Casey had a few Pentomino pieces on his desk, and I desperately felt the urge of puzzling with them. But that's me. But likewise, like doors do this, questions afford to be answered. So when I say as a computer, where should I put the puzzle piece, then the human is going to think, okay, I have to answer to this question, so I have to describe the location where to put the puzzle piece. Motion, as a third thing, manifests the possibility of interacting with that motion, and we call that steering. And steering is super easy. So if I move something, you can say, no, stop moving. Okay. So steering is super easy, especially on a 2D plane. You can go up, you can go down, left, right. You can go diagonally, you can stop, you can reverse, and so on. But it's a very closed vocabulary. So that will radically simplify our task, at least if the human keeps up the steering metaphor. And we found that the computer has to be quick, right? I steer, and there has to be a reaction to it for this to work. So I'll show you a video of one of these interactions. Please focus on A, how swift the system reacts, and to some extent try to look at the error recovery. You will see ASR results. They will be in German. I will be speaking German in that video. Don't worry about it. And also something weird may happen with this video, and it will not be online, but I can put the link somewhere.
Weiter links, nach links, ganz links.
All the way to the left was what I said.
Jetzt runter, stopp.
Down, stop.
Platzieren.
Where should I put it?
Rechts.
Right.
Noch ein bisschen höher.
A little up, Up, up. Up. Now it works.
Nach oben, hoch. Ja, noch ein bisschen. Weiter rechts. Noch weiter rechts. Stopp. Jetzt hoch. Stopp. Etwas runter. Stopp. Hoch. Stopp.
So, what did you notice? This. Sorry, it doesn't. No, it doesn't understand German very well. This is what happens when Timo trains ASR systems in the actually early 2000s. Yes. So it doesn't understand German very well. Okay, but what else? There is a delay? Oh, not very much. Okay. So when you say it doesn't understand German, does it understand orders?
What do you mean?
Like when I tell it to do something, does it do something?
Yeah.
See, and that's the point. Every dialogue system, like every conventional dialogue system that you could see out there, would be much better at understanding the orders that I give, but it would be way slower. So here was actually a mistake that happened because there are different words for saying up, and we only had one in the understanding module, and it turns out it sounded like there's also a word for up that sounds kind of like down. So it only understood down. And likewise with left and right, and I frequently got those wrong. I would say go to the right, and it would immediately go to the left. But that's the point. Users actually don't feel as lost here because the fundamental principle, user tells the system to do something, system does something, that's held up. However, like this lowest, this lowest interaction layer is working fine. However, the system is stupid, so it does do the wrong thing frequently. But the point is basically, so we tested that. They all picked up on the affordance of motion. They were significantly faster in the version where it kind of like immediately led to the steering metaphor. And there was people liked this, affordance of motion. the system was rated as more transparent and reactive. And the point is actually the ASR errors, they inhibit the understanding, but not the interaction itself. It's kind of like contrary to what most people are working on. And of course I've since fixed this issue. The point is basically it keeps you in line about how things move along, and you get the impression not that the system is unwilling to help you, but that it's unable to help you, which is far better. I want to talk a little bit about spoken output based on incremental processing, and I threw in this using under specification because we were talking about that as a reminder for me to focus on that part. So your standard speech synthesizer will actually, or speech generation pipeline will start with a pragmatic plan, break that up into phrases, come up with ideas what to say, come up with words, in this case German words, we'll work on the syllables, phonemes, and eventually give you speech audio. And then it will start speaking. So it has done a lot of work. Well, maybe here the user hangs up. So that's not really useful. And also, like back in the days, it was slow. So it easily gives you a delay of 2 seconds just for processing before you speak, and then you don't do nothing while speaking for 8 seconds. So rather, let's put all this processing time into the speech time than do it in between. So an incremental system, you would not bother about the third phrase yet. You need not really bother about, what word you're going to use for take. All you do is, you start down here, and then you can start speaking, and then you just have to be sure that you come up with the other stuff in time to continue speaking. And the point is, again, we do this global stuff, or the traditional systems do the global stuff, so that they have more context and the speech quality is better. So there are 2 things. One is to degrade gracefully if little material is available. So of course speech quality is probably not going to be as good as it could be if you knew the full context. Right? You might have to pronounce the beginning of the book differently if only you knew the very end of the book. So you want to degrade gracefully rather than just completely sucking. And you must have the ability to extend the structure just in time. And when you have such a thing, extending the structure can happen in multiple ways. You might learn more about the domain, what to put and where to put it. You might, up here, notice, I don't know where to put it. I have to say a hesitation, like, take wait, let me see what to take. And of course you have this real-time demand here from the bottom. So integrating all these things is actually the challenge on the output side here. And that is actually works. I want to show you with an example here. So luckily the same domain that you already know, I can take colorful crosses, T's and long pieces, and I can delete them. And you'll have to notice me clicking now, and this is like, kids love this on science night. They click here, and they have to click here and time, or any combination of those, for the system not to say, oh, I don't know what to say. So I can say, I was too late. And as you notice, speech synthesis can sound better nowadays, but this is what we were stuck with a few years ago. So here you see kind of like these extensions coming from the top, and this R being kind of like a thing, what it does when it doesn't know what to say anymore. We use that in an application to change our mind while we're speaking. And in this case, say less when people react. We used the domain for social robot navigation and looked at personal space intrusion. That was the colleague of mine, Felix Lindner, working on that. So personal space intrusion is usually something that robots avoid because it's kind of not not a good thing to do. But then again, in this situation, or highlighted here in this situation, there's actually no choice, right? The robot really needs to go here. There is no room behind. This is kind of like the personal space between me and this funny thing on the wall that I'm reading. But it really needs to pass. So standard social robotics would tell you that whenever you find yourself in the social space of a human, stop. Doesn't sound extremely human to me. Or try to avoid social space at all costs, which doesn't sound very social to me, rather asocial. So our idea was, if you have to do that, then apologize and explain yourself. Simple enough, right? I mean, so we built a system, or we built this little robot. Those are the speakers I was talking about. So in this example, you might not see that I'm wearing headphones. The robot kind of wants to pass along here. And in one case, I'll be wearing headphones, so I don't hear it. I don't react. So it'll actually excuse itself very elaborately. And in the other case, you'll just see what happens. Oh.
Excuse me, I want to pass urgently to rescue a patient from the
That's not a hospital in Germany, it's just a university. Don't worry. So if I move...
Excuse me, I need to pass
it'll just, abbreviate what it's saying in a smooth way. And it turns out that standard robots wouldn't be able to do that, and you'd be surprised why. So, of course, that was a nice video. I could, just for the effect, I might dance around a little and people would like it better. We had a simulated robot environment. We had different robot speeds and human movement conditions, different speaking conditions. Either the robot didn't say anything, or he did the long thing, or it would just skip forward to thank you when the personal space was exited. So you could say, I need to pass, thank you. I need to pass urgently to rescue a patient, thank you, and so on, all these variations. We showed that to students that we had, and rated the naturalness, politeness, and the route and the speed of the robot, just as a control. Whether people would, prefer the speed of the robot that was silent, maybe. Turns out there was no effect on that. It was just a control condition. But we did find results for naturalness and politeness. So in particular, a robot that is incremental or doesn't speak is natural. So this one wasn't really natural. Or a robot that says this long sentence or the short sentence is polite, but not saying anything would be unpolite. So if you want to be both polite and natural, you actually want to follow this incremental strategy. All right. So I'm going to give a final example about what I've been doing more recently. For a full-blown dialogue system, like my strategy used to be build tiny little dialogue systems that show exactly one thing and sort of show off incrementality because that's what I'm good at. Now I'm working in a larger project and we have this movie recommendation agent that is trying to be social about recommending movies, and it really wants to engage you into that topic, and there's all sorts of things from vision tracking, emotion or conversational strategy inference, social reasoning, and then choosing its own conversational strategies to go along with that. So what we do there is kind of like a lot of things, and they're all non-incremental, and it's all doomed to fail, in my opinion, anyway, if it's non-incremental. So we would be saying things like, this is a movie you're going to like. It's called Titanic. Or we might say things like, oh, even you might find that funny. Or, wow, given your given your excellent criteria, I found this movie, it's called Titanic, and so on. Depending on the conversational strategy that our system has, it's going to say what we call, this social sentence, and afterwards actually gives you a recommendation. So as you might notice, the conversational strategy is relevant for this, and we don't really need to know the movie to kind of, praise the user or kind of try to bond with the user. We only need it for the second sentence. So what we started with incrementality here was to rather wait until we have found the movie, and this movie recommendation system is just embarrassingly slow, but really good. We can start saying the social sentence immediately. If we just pass on the information, now we're going to recommend a movie. It's called X, and that's capital X. It's a variable. Let's later deal with what the value for this X is, and then we can actually cut down the time that we need between the user is done speaking and when we answer. So something like 2 seconds at the beginning of the summer. So that was another crew student actually this summer. So we can cut down these 2 seconds to something like 300 milliseconds if we don't bother about finding the movie just yet, because we can start talking, and we could even say it's called without having any idea about what it's called, just as long as we figure it out in time. So in this larger scale system, we had to change around a few things, but actually surprisingly few, by kind of making use of the fact that we can just pass along a variable without knowing the name, by subclassing this slot to contain a variable, and by when we try to access the variable content, just doing the callback then and hoping that we know the information until then. And it's like most of the time we actually still have to wait because speaking this first sentence already takes some time. And then we checked in the user study whether this is better, and the first answer is yes, of course. We cut down the waiting time so much. So, I mean, you saw that in the slide before. Of course, the waiting time is shorter, so objectively we're fine. But we also asked everyone, like in the debriefing phase, so you may have noticed, one of the systems, it was either A or B, was much faster than the other. They were like, really? I didn't notice. Or like, yeah. And then you'd ask, so which one was it? And it was basically random guessing. They did not consciously notice which one was faster. They didn't have a clue which one of these was 2 seconds slower per turn. And people had told me this before, and I was like, no way. People will notice which one's the faster system. But we also asked a lot of questions. And now we see significant differences in terms of the responsiveness, the attentiveness, the enjoyability, and particularly, which triggered the title of today's talk, the task quality. People preferred the movies that were recommended by the faster system over the movies recommended by the slower systems, although we haven't done anything with the movie recommendation. So this is kind of an interesting aspect when you're designing dialogue systems and you want to be want to have user reporting good performance of your system or good task performance, make it faster. It's also scary when you ask people, how do you like that movie? Because the answer is not going to be about how much they like the movie, but it's probably going to be how much they like the setting in which they were asked about the movie and got the response. So that's kind of like a faster response will also mean that you're better. But if you haven't changed anything, you actually know you haven't done anything better. So that's kind of like an interesting aside. But apart from that, we actually made it better and more responsiveness, more enjoyable, more attentive, the things that we expected. Like when we set out asking about the movie, we were also pondering this might go awry because people could say, well, that thing was just shooting out any movies at me. It didn't really ponder my request. It just gave me a reply quickly. So it could have gone the other way, that people say, no, movies by this system aren't as good because it's not really thinking about it. But it turned out to be, people like it better, probably because they don't consciously notice this timing difference anyway. So to summarize Responsiveness to the interlocutor is a key issue in spoken interaction. So if you're interacting, you want to do it quickly. If you're a computer, you actually want to do it super quickly as you can. And at least so far, we haven't seen a system that was too quick. At least I haven't. Maybe I've missed the sweet spot. So people were saying to me, why would you want incrementality? Maybe people don't want the responses so quickly. I was like, okay, I can test that. Once I've got the quick system, I can delay it, and we'll see. But so far, like, the results never indicated that I should, be slower than I can be. Incremental processing is a fabulous way of enabling responsiveness. It means, to take actions based on partial knowledge rather than full knowledge, and then to remain flexible to revise actions that are already in execution and change what you're doing as you're doing it. In terms of integration, what we've been doing more recently is layering rather than pipelining, moving together speech recognition and speech synthesis, or natural language understanding and natural language generation, rather than having these far apart. And that's about it. Thank you.